Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome to Week 2, Lecture 6 of Dynamic Atomic Force Microscopy Methods. In the last class and the classes before that, we've been focusing on the analytical theory of how we can link the observables in dynamic atomic force microscopy to the operating conditions of the microscope and the forces that are experienced by the tip, the sensor tip or the cantilever tip in the microscope. In particular, there were two very important results we talked about last time. One was the possibility that when we focus on tapping mode atomic force microscopy, that the varial and the dissipation can adjust in a manner that one can actually get two solutions that can coexist at the same amplitude, but at different z distances from the sample, which leads to a certain kind of instability, and we demonstrated examples of that in the literature. And the other thing we focused on was the notion of what phase contrast means. And what we concluded regarding phase contrast was that the numerator of the phase contrast contains the dissipation term, and the denominator actually contains the varial term. And so that the numerator and denominator, the energy dissipation and varial, are actually not independent in tapping mode atomic force microscopy. They're related. Whenever energy dissipation becomes higher, the z value adjusts itself so that the varial becomes smaller, and vice versa. Based on this, we concluded that when one looks at phase lag, and if you've taken your entire image in the repulsive regime, then parts of the sample that show greater phase lag would actually correspond to more dissipation on the sample, and of course correspondingly less varial on the sample. Generally speaking, that translates to, in cases where the prime surface physics of dissipation is due to viscoelastic repulsive interactions, this would imply that phase lag would be brighter when you're imaging in the entirely in the repulsive regime on softer and more viscous samples. On the other hand, we talked about the fact that if you have taken an image entirely in the attractive regime of oscillation, if your entire image is in the attractive regime of oscillation, then brighter phase lag actually means lesser dissipation and more varial compared to darker areas. But in most situations, when we're doing phase contrast, we tend to operate the microscope in the repulsive regime. And even in the repulsive regime, one really needs to understand or have an idea of what is the main source of dissipation in the sample in order to really understand what one is getting. What we're going to talk about today are two additional important quantities that the analytical theory of AFM is able to give us some insight into. So what this slide shows is it's sort of a map of what are the observables and the non-observables in dynamic atomic force microscopy. Observables are those quantities that we directly measure in the microscope. This would, for example, correspond to the amplitude far from the sample, set point amplitude, the drive frequency, the amplitude and phase as you're scanning the sample, or if you're doing frequency modulation, frequency shift and excitation signal. And these are all quantities which you can observe. And as we will talk about briefly today, we will also be able to, and most commercial AFM systems will allow you to actually also map the average force that you apply in the sample. Now, the amplitude and phase can be converted very easily into energy dissipation and varial, like we talked about in the last couple of classes. So these are all, broadly speaking, the observables that are based on cantilever dynamics. On the other hand, there are some parameters, calibration parameters typically, such as cantilever stiffness, Q factor, which we've discussed how you might actually determine those for your particular probe. In contrast, as you're scanning over a sample, what remains unknown is what exactly are the interaction forces between the tip and the sample as a function of time. We talked about the fact that as the tip oscillates and clumps close to the sample and moves away. There's a small interval of time in which there is an interaction with the surface, and the actual profile of how the force changes between the last few atoms in the tip and the first few atoms in the surface is actually not observed directly in tapping mode AFM. The other part of this profile of this interaction force would be the peak force. What's the maximum force that you actually apply when you are tapping on the sample? These are all what we would consider as hidden observables or non-observables or hidden variables, let's say. And it's quite different from contact mode AFM, because in contact mode AFM that we studied in the first part of the class, you actually prescribe a set point force at which you want to image the sample. So in that case, you actually know what force you're applying on the sample. In tapping mode AFM, we don't know what force we're applying on the sample. It's a hidden variable. We know what amplitude we're applying or imaging at. So we're going to focus first on the average force. I mentioned in the last slide that average force is technically more of an observable, because most commercial AFM systems actually allow you to measure the average deflection of the cantilever, and the spring constant times the effective deflection, or the average deflection of the cantilever, is in fact the average force between the tip and the sample. Nonetheless, we're going to start there to really try and understand what does the average force really depend on. So what I've shown here is a one cycle of oscillation of the probe tip of our point mass oscillating model. And just before that, just underneath that, rather, I've sketched out the interaction force history that the tip experiences as it oscillates and interacts with the sample. What I've done in blue, I have basically done the decomposition, the additive decomposition of conservative and dissipative interaction forces. The blue curve is actually the conservative interaction force, and the green curve is actually the non-conservative interaction force, or the dissipative interaction force. The difference between the two, of course, is that the conservative interaction force depends only on the tip sample gap. It doesn't matter if you're approaching or moving away, which is why you get a symmetric profile about the peak value. On the other hand, the dissipative part is purely dissipative in that the force value approaching the sample is actually opposite in sign to the force value when retracting from the sample. So we're going to talk about the average force. And let me go over to the board and try to walk you through a couple of key steps in the derivation. Like I mentioned to you, what I've plotted out here is the conservative interaction of the tip sample interaction force as a function of time. This is the dissipative component as a function of time. The conservative component is actually symmetric about its peak value, because the conservative interaction force depends only on the tip sample gap. So when you're on either side of the peak, you're at the same gap from the surface. As a result, the force value must be the same. On the other hand, the dissipative interaction force is actually antisymmetric with respect to the peak force point. Now, the actual interaction force between the tip and the sample is the additive sum of these two. So when we're trying to take the average value of this force over the oscillation cycle, the average value of the interaction force is going to be the average of the conservative plus the average of the dissipative component. But when you look at the dissipative component, you see right away that this is antisymmetric. So this area out here actually cancels with that area. As a result, the overall average of the tip sample interaction force must equal the average of the conservative component only. The average of the conservative component is simply going to be the area of this divided by the total cycle time of oscillation, and you might end up with an average value that sits out here. Now, in the appendix, I have derived an approximation of this average force based on an article by San Paulo and Garcia, which makes a couple of assumptions. One, it does assume that the tip sample dissipation is negligible, and it assumes that the contact time, or the time during which the tip interacts with the sample, is very small in comparison to the overall oscillation time. These conditions are relatively common when one deals with very high set points, gentle imaging conditions, and under those conditions and relatively moderate to hard samples, this approximation would be a reasonable estimate. A key result, again, that I've described in the appendix, this is able to derive or approximate the average force encountered in tapping mode AFM using the formula 1. And what you see in equation 1 is a pretty interesting result, in that, rather surprisingly, the average force does not seem to depend on the local properties of the sample. It in fact does depend on the spring constant of the sample, the amplitude of the oscillator far from the sample, the Q factor of the oscillator, and the set point ratio at which you choose to operate it. The other thing one would notice is that in general, as the set point amplitude decreases, the average force tends to increase as you come closer to the sample. When we start looking at peak forces, we'll see that this tendency becomes quite different. So the implications of this result are that, at least to first order, when one tries to describe, the leading order effects of average forces and its connections to local properties, that the average forces tend not to depend on local properties, but rather depend just on the cantilever and the operating conditions at which you operate the microscope. So this brings us to an interesting question as to how is it possible that when you're scanning a sample with a microscope, you might be interacting with different kinds of materials, softer, harder materials, and yet how is it possible that the average force remains constant as the formula suggests? The way to think about this is, again, shown in a couple of sketches that I've shown out here, is that when you look at the tip-sample interaction force as a function of time during an oscillation cycle, if you're on a hard surface, we expect the interaction time to be very short. We will also expect the peak forces to be very high. And when you're on a soft sample, on the other hand, we're expecting the interaction forces to be longer, since the tip will spend more time in the sample, but the peak values of the force are going to be smaller. So what the formula suggests is that, at least under the conditions under which that approximation is valid, that when you transition from a hard to a soft material, all that happens is that the interaction time changes, the peak value changes, but in a way that the average value of the force is more or less constant as you scan over the sample. So this is a very important result, and it helps us think a little bit about what's the relative role of interaction forces and peak forces when we're talking about different kinds of material properties. The other thing to notice from these little sketches that I have out here is that the average force value is going to be typically much lesser than the peak force value. The peak force value can be sometimes even 10 times larger than the average force value. Which brings us to the question of what are the peak forces? Because, as I just mentioned, peak forces are going to be the maximum force that the tip applies to the sample. And clearly, that's the force that we want to reduce on the sample, usually, because we want to reduce damage to the sample, reduce the stresses applied during tapping on the sample. On the other hand, under certain conditions, we may actually want to increase the peak forces, especially if we want to see contrast or phase contrast due to viscoelastic dissipation due to repulsive interactions with the sample. So the peak force becomes an important hidden variable or non-observable in tapping mode AFM. And the main question here is, what can we do to understand what are the different factors that govern the peak forces? Now, there are many different ways of going about it. There's been some attempts at actually using experimental methods to directly measure tip-sample interaction forces. Those methods usually involve specialized cantilevers or specialized data processing techniques that are not available on all commercial AFM systems. One can also do numerical simulations, but numerical simulations don't really give us necessarily a feel regarding how these peak forces change if you change operating conditions or cantilever properties and so on. So what I'm going to describe to you today is first how you would approach it using numerical simulations, and then we'll talk about approximations that you can make to understand what the peak forces in dynamic AFM are. To do simulations, one would resort to VEDA, which is the virtual environment for dynamic AFM. And what VEDA does, as we'll be discussing in the next week of classes, it is an online simulator that's available to simulate not only dynamic AFM methods, but also static AFM methods. In the dynamic AFM methods, what it basically does is, in the basic tools, it takes the point mass oscillator model with many kinds of tip-sample interaction forces. It allows you to construct samples with different tip-sample interaction force profiles in different locations, scan them at different proportional integral gains, or approach them with different operating conditions, and so on. And it's a Fortran-based code, so it's very accurate, and as I mentioned to you, it allows a very large number of tip-sample interaction parameters. So what I'm going to show you next is a simulation that's been performed in VEDA. The details of the parameters for the simulation are actually shown in the appendix. But what's been plotted here along the y-axis is the tip-sample interaction force history in nanonewtons as a function of z, which is the separation distance, as an oscillating cantilever is made to approach the sample. The properties of the cantilever are shown. It's a moderately soft to moderate stiffness cantilever, 50 kilohertz, with a free amplitude far from the sample of 25 nanometers. And it's approaching a softer sample. The tip-sample interaction model is the DMT interaction model. Again, the details of the parameters used for the simulation are shown in the appendix. Well, what you see is basically a history of what kind of tip-sample interaction forces one encounters as one approaches the sample. On the very right, the value of the force is 0, so the time-varying forces are pretty much 0. But when you start approaching the sample and reach a z value of about 26, 27, one starts noticing that there is a dip in the envelope of forces, and if you zoom in, as I've shown on the bottom right, you find that the tip is basically in the attractive regime. It comes to near the sample, goes away, and the interaction force history is all negative in that the tip dips into the attractive part of the well, comes out, always having a negative interaction force. And the peak value of that attractive force has been indicated in that little window on the bottom right. As one approaches the sample further at a z value of roughly around 25, one notices there's a transition as the tip of the microscope jumps from the attractive regime of oscillation into the repulsive regime of oscillation, and now it's experiencing positive interaction forces as well. And what I've shown you is at a certain value of z, at about z equal to 15 nanometers, I've zoomed into the force history in the simulations, and you can see that the tip-sample interaction force history appears to be and a little attractive as you approach the sample, and as you move away, there's a sharp repulsion, or as you go a little deeper, there's a sharp repulsion, and then there's a reflection of that as the tip moves away from the sample. So you get a pulse-like tip-sample interaction force, which repeats itself every cycle of oscillation as one comes closer to the sample. The highest value of this profile of interaction force, as indicated in the figure on the top right, is going to be the peak repulsive force of interaction. So, when we go ahead and try to do simulations of this, we can repeat this for many different parameters, and what you see out here is a whole bunch of different parameters under which you can do simulations. Again, we're using the DMT interaction model, and you see that one is changing the cantilever stiffness from 1 to 200, the Q factor from 50 to nearly 1,000, Young's modulus of the sample going from 0.01 GPa to 100 GPa, the free amplitude, or the amplitude far from the sample, changing quite a lot, the Hammacher constant changing quite a lot. All these different numbers, when one does different simulations, are plotted on a log scale along the y-axis below, the peak repulsive force that's encountered, and along the x-axis is plotted the amplitude ratio, where amplitude ratio equal to 100% means we're just starting to engage the sample, and as you move in to 50%, you're reaching 50% set point and coming closer to the sample. The y-axis is plotted on a log scale, but what you notice is something very, very interesting. One notices that the peak forces tend to increase, reach a maximum value at some intermediate set point ratio, and then they decrease again. This is very different compared to what was predicted for the average forces. Remember, the average force equation suggested that as the set point amplitude decreases, the average force just keeps on increasing. In this case, on the other hand, it's very clear we get a very interesting regime where the peak forces increase as you reduce set point, reach a maximum value, and then they start decreasing. So the maximum peak force that one would apply is not at the smallest set point ratio, nor at the largest set point ratio, but at intermediate set point ratios. This is an important finding which is used very often in trying to enhance phase contrast in polymer blends, for example. So the main question is that when one looks at all these simulations, one notices the peak force values tend to be distributed over 4 orders of magnitude depending on all these different cases that we have simulated. The key question is, in spite of the fact that we simulated these under so many conditions, the rough behavior, qualitative behavior, is roughly the same in that they reach this maximum value and go down. And the question is there an underlying formula that tells us this general trend of interaction forces or not? And in this article that I refer to out here, and the details of how one might actually go about doing this are again given in the appendix. There's been simple formulas for the peak interaction forces that have been derived for relatively straightforward tip sample interaction models. In the case of pure Hertzian repulsion, for example, the peak interaction force formula is shown here. What one notices is something very interesting in the result. It clearly shows that the peak interaction forces depend on the amplitude ratio in an interesting fashion, in that when the amplitude ratio is 0, which is when you're very close to the sample, or when the amplitude ratio is nearly 1, when you're just starting to engage the sample, the value of the peak force in both cases is actually 0. And then somewhere in the middle, you're going to reach a maximum value. Outside this dependence of the amplitude ratio, we find an interesting dependence to the 1/4 power of the elastic modulus of the local modulus of the sample, which means that the greater the local modulus of the sample, the more the peak force is going to be. But what this really tells us is that everything else being the same, which means cantilever operating conditions, cantilever properties, when one goes from part of the sample where the Young's modulus is, let's say a value of 1 gigapascal to another part of the sample which is 10 gigapascal, the peak forces between the two situations will scale by 10 to the 1/4 power. So not as much as the actual change in modulus is. It's going to be a little lesser. So you may expect, for example, when you go from a 1 gigapascal to a 10 gigapascal part of the sample, the peak forces may have increased by a factor of about 2 or 3. So these kind of scaling laws really make it very easy for us to estimate how the local properties in the sample actually affect the peak forces that one is likely to encounter. It also shows, for example, if you want to reduce the peak forces, you want to have a cantilever with a large Q, small k, and you want to reduce the free amplitude as much as possible, which scales down the peak forces. If you want to maximize the peak forces, you of course can do the opposite, choose cantilevers with large Ks and low Qs, and you would choose set point ratios that are roughly between 50 and 60% as indicated here. That will actually maximize your peak forces. So when you take this and go ahead and try to put all these results together, you find that the predictions from this formula actually, when you scale them properly, they basically get you, within about 10 to 20% of the simulation results under all these conditions that I showed in the previous slides. So it's a pretty reasonable approximation. You wouldn't use it for quantitatively predicting exactly what you'll be getting, but it tells you how these peak forces really change and scale with operating conditions, local properties of the sample, and so on. So the key thing again is that the max forces are achieved at a certain intermediate set point ratio between 50 and 60%, and that the results that we have shown using the scaling law are pretty good as far as you're using them in vacuum conditions or under ambient conditions. Under liquid AFM conditions, these maximum force formulas can become quite different. So thank you very much, and we'll continue in the next lecture to introduce Veda and how you can do these kind of simulations to answer a lot of questions. Thank you.